If you would recall, last week we brought up the fundamental theorem of calculus. We didn't record about it, so we should record about it now. So last week we brought up the fundamental theorem of calculus, both parts of the fundamental theorem of calculus. To build dramatic tension, most books split this up into two different chapters. They're both related. It's both parts of the fundamental theorem of calculus. Let's just do them all at once. So fortunately, I'm not run by a major studio that says, hey, this will make 3 movies. And you're like looking at The Hobbit, Michael, dude, this is barely going to make 1 movie. It's like, oh, no. We're going to make 3 movies out of it because everything has to be trilogies. So fortunately, the fundamental theorem of calculus is immune to that because there's only 2 parts. So I guess studios did just kind of like say, well, we're going to make 1 movie into 2 movies because money. But that's all beside the point. Here's what we want for the fundamental theorem of calculus: a continuous function on a closed interval. So this is something that we can apply to any continuous function on a closed interval. C is just any value from the closed interval. And since C could be from the closed interval from A to B, C could be A or B. So the first part has to do with definite integrals. The first part says that you can calculate a definite integral with an antiderivative. The definite integral from A to B of f of x to x is capital F at B minus capital F at A, where capital F is an antiderivative of little f. That is capital F prime equals little f. Once again, what we're doing is we are calculating a definite integral with an antiderivative. That's the first part of our fundamental theorem. The second part of the fundamental theorem just goes the other direction. It says that a function defined this way, if we say capital F of x is the definite integral from c to x of f of t dt, this will be an antiderivative of little f of x. What we're doing here is constructing an antiderivative with the definite integral. This is a big deal because it means that we can this is a big deal because we can approximate definite integrals just with area. That's what we base the whole idea of the definite integral on. The idea of length times width, but length is continuously variable. So that's why this is a big deal. Number one, we can approximate a definite integral with area to any degree of accuracy, given enough computing power and data. And this is important because some functions do not have nice antiderivatives. Remember that by nice antiderivatives, we need a finite combination of elementary functions. Since some functions do not have nice antiderivatives, they're not the derivative of any finite combination of elementary functions. It is very useful to be able to construct those antiderivatives using the definite integral, because the definite integral can be approximated by area to any degree of accuracy for a continuous function, given enough computing power or data. So here are the 2 parts of the fundamental theorem of calculus. We're relating the definite integral to the antiderivative. What that means overall is that differentiation and integration are almost inverse operations of each other. That's the other thing that we're relating here. Derivatives show up because I keep using the word antiderivative, which is just derivative going the other direction. Any questions? So when someone asks you what calculus is all about, actually the fundamental theorem is not the thing that you'll want to bring up, which is weird that we call it the fundamental theorem and it's not the thing that you want to talk about when you talk about calculus. If you want to sound all esoteric when someone says, what's calculus about? You should be like, oh, it's the study of infinity, the rigorous study of infinity. And when they're like, oh, well, what does that mean? Well, it's the calculus, it's the mathematics of change. Even if you start explaining it to them, for the most part, that goes over people's heads. But for the most part, people look at you like, oh, that's a little bit esoteric, don't you think? And you're like, oh, no, why do you ask? They're like, oh, you know what? They'll just drop it at that point. You just be like, well, it's a math class. It's the last pre-math class before you start doing math. Right. So all this is relative, is talking about integration, these definite integrals, and this antiderivative business. So one of the things that we want to do, we want to be able to find antiderivatives, and we also want to know when we can't find antiderivatives. The handy thing is that if we get stuck, we can always just build our own antiderivative. Kind of like all those videos on YouTube, how to build tools when you don't have a particular tool. Usually it's overdone and the amount of effort required is greater than the amount of effort it is to just like hop on over to a hardware store and pick up the thing that you need and then go back. But that depends, because you'd also have to have the tools to build the tool. Like it's one thing if you're going to make your own hammer, but think about what's required in making your own hammer. You'd have to have a forge and a bunch of metal. And at this point, it's easier to outsource the manufacture of the hammer to a company that can make millions of hammers so they can do it very cheaply rather than make your own hammer. Usually at the point where you have to nail something in and you don't have a hammer, you just grab your heaviest flashlight. But then they've messed up flashlights by putting the button for the flashlight on the back of the flashlight. I'm like, oh, that's the hammer end of the flashlight. And Maglite is just shaking its head. Flashlight's a lot less intimidating now because we're just better at making batteries. So you don't need a Maglite that has like 15 D batteries in it. So it just like becomes by default a weapon. You know what I mean? Now you can get a very effective flashlight out of a smaller battery using LEDs. But it's like, oh, this flashlight is better than my 15 D cell Maglite. Unless I need to whack someone with it. Then it's like kind of useless. You know what I mean? That's why I went on Shark Tank. I'm like, oh, this is my new flashlight. I noticed that there was a decrease in offensive power in the flashlight, so it's also got a switchblade in it. And they're like, oh, you know that switchblades are illegal? It's like, oh, well, I'm gonna have to switch to plan B if you're not gonna fund my thing. I have a switchblade, give me your money. Pro tip, don't try to rob people when you're taking a television show. It never works. Also, millionaires don't carry money around, so what a waste. Anyway. What are we talking about? Oh yeah, and even if they had expensive watches, what are you gonna do? Like someone quick, tell me, I've got a $20,000 Patek Philippe watch. Where do I sell it? That it doesn't get immediately found. Like my favorite car theft story is the dude that stole Guy Fieri's Lamborghini. What are you going to do with a Lamborghini? I mean, joyride, obviously, but how can you just joyride a Lamborghini? It's super noticeable. There's a reason that like you steal Honda CRVs because who's going to know? Honda CRV owner will walk out to the wrong Honda CRV. It's like, oh, that's not my silver Honda CRV. I've got 5 more to check in the parking lot. You know what I mean? But if you've got a bright orange Lamborghini and someone steals it, it's like, oh, what's the license plate? Who cares? It's a bright orange Lamborghini. Just look for the nearest bright orange Lamborghini. It's probably the one that's missing. You know what I mean? Anyway. What are we talking about? Oh, yes. Fundamental Theorem of Calculus. We need to learn how to find some antiderivatives. On the outside, we need to find antiderivatives so we can calculate definite integrals. But we have machines that will calculate definite integrals to pretty much any degree of accuracy, and some of them will even find exact values for us. So that's not really the point. Fortunately, half of the work has already been done. Everything that you know is a derivative is now an integral. All those derivatives you know, so the good news, half the work has already been done. You've already been working on finding antiderivatives. All your derivative formulas are now antiderivative formulas. All your derivatives are also antiderivatives. So here's a derivative that we know, the derivative of a power function. The derivative of x to the n is nx to the n minus 1. We multiply by the exponent, then subtract 1 from the exponent. We also have an antiderivative of x to the n to x, where we do the inverse. We add 1 to the exponent and then divide by the new exponents. This only works if n is not -1, because otherwise we'd be dividing by 0, and we're not allowed to divide by 0. Try to divide by 0, the math cops come and arrest you. A bad day for everybody. Everybody remembers that show, right? Math Cops. It didn't last as long as regular Cops. Had a theme song and everything. Math Cops. What you gonna do? What you gonna do when you divide by 2? It's a whole show. No one remembers it? Maybe I hallucinated the whole thing. So this add 1 to the exponent, divide by the new exponent doesn't work if the exponent is -1, but that's okay, because we also know the derivative of natural log. So it's all because we know these derivatives. The derivative with respect to x of the natural log of x is 1 over x. And so that means that the antiderivative of 1 over x dx is natural log of absolute value of x plus c. So we have it taken care of when n is equal to -1. So that's all okay. Note that when we're going in this direction, we have the natural log of the absolute value of x. This is to avoid domain problems. 1 over x and natural log of x, neither one is okay with x being 0, but natural log of x is not okay with x being negative either. But 1 over x is cool with it. So we put the integral of 1 over x dx as natural log of absolute value of x to make the domains work out. So this is to keep the domains happy. So if I ask you to integrate natural log of x, you got to write integrate 1 over x. You got to write natural log of absolute value of x. Otherwise, I take off 1,000,000 points. And right now, if you lose 1,000,000 points, you go all the way back to elementary algebra. You have to do all those classes over again. I'm just kidding. That would be, no one does their MMOs that hardcore anymore, where like character death means losing experience points. So what we want to be able to do is take all of the derivative things that we have and make sure that they are also antiderivative things. So the derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x plus c. So we got to remember that when we're integrating, we got to put back information that was lost. The derivative of any constant is equal to 0. So if we're looking at e to the x, it could be the derivative of e to the x plus some constant. That's missing information. The derivative wipes out all the constants, become 0. We need the variations on this as well. Remember, we're playing the inverse game. So if we had a constant, e, the derivative of e to some k times x, here we have the simplest application of, actually the second simplest application of the chain rule. The derivative of e to some constant times x, we know is e to the kx times the derivative of kx, which is equal to k. So we get k e to the kx. So what that means is if we multiply by k in the derivative, and then we're going to do the inverse in the antiderivative. We're thinking of the antiderivative as the inverse of the derivative. Questions? It's only going to seem like a lot to remember because it's a lot to remember. You have to remember all of it all the time in perfect detail. So no problem. No pressure. There are a bunch more derivatives that we know. The derivative of sine x is sine of kx is cosine of kx times the derivative of kx, which is k. So if we invert this process, instead of multiplying by k, the constant, we'll divide by k, the constant. So the integral of cosine of kx dx is sine of kx divided by k. Plus c for our constant of integration. All our derivative information is now integral information or antiderivative information. The derivative of cosine of kx is minus k times the sine of kx. That's what we knew before. We're just adapting this to the new thing that we know now. The integral of sine of kx dx is minus 1 over k cosine of kx plus c. We're just taking all of the derivatives that we know and turning them into antiderivatives that we know, or indefinite integrals that we know. The derivative of tangent is secant squared. That's how we remember it. That's not how we write it, because tangent by itself doesn't mean anything. The derivative of tangent of something is secant squared of that thing times the derivative of that thing, which is k in this case. Since the derivative of tangent is secant squared, the integral of secant squared is tangent. Since the inside has k, when we're taking the derivative, we multiply by k. So when we're integrating, we divide by k. This is because the derivative of the inside is just a constant. So we can just bounce it around wherever we want. The derivative of secant is secant tangent. So the derivative of secant of k times x is k times the secant of kx times the tangent of kx. So the integral that we'll look for here is the integral of secant tangent. So the integral of secant tangent is secant. We're just turning it around. All the derivatives that we knew are now antiderivatives that we know. We know the derivative of arctangent of x is 1 over 1 plus x squared. So the derivative of arctangent of kx is 1 over 1 plus the square of the product of k and x times the derivative of kx, which is k. So the integral of 1 over 1 plus kx squared is arctangent of kx. All the derivatives we know are now integrals we know. Any questions? Is everybody okay? Hard to tell. It's like Monday, and all it's kind of like. And that means a couple of things. It means like, I don't remember these derivatives at all. And it also means like, well, yeah, I remember all these derivatives. A little bit of both. With a dash of Monday. And the realization that it's week 10. And that's also a little bit of both. It's already week 10, but also simultaneously, it's only week 10. How many weeks are there? 18 includes finals. So 17 weeks, then finals. I think there's one more derivative that we know. No, I dropped the K's. That's fine. I just realized I need to drop the K out of this one too. Let's just remember it this way. Integral of 1 over 1 plus x squared. We'll deal with the K part later. Like next semester later. So the derivative of arctangent of x is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared is arctangent x. The derivative of arcsine of x, I realize that I don't really have the words with the K. It really messes up my brain. So I'm like, oh, the derivative of arctangent of x is 1 over 1 plus x squared. The antiderivative of 1 over 1 plus x squared is arctangent of x. The derivative of arcsine x is 1 over square root of 1 minus x squared. So the integral of 1 over the square root of 1 minus x squared is arcsine x. All we did was take the derivatives that we know and reframe them as integrals. If we really understood our times tables, this is how we could understand division. This is how division and multiplication are related. Knowing that 2 times 3 is equal to 6, we get 2 other pieces of information for free by understanding that division is the inverse of multiplication. Since we know that 2 times 3 is equal to 6, we also know 6 divided by 2 is 3, and 6 divided by 3 is 2. It's like we get 3 pieces of information for the price of 1. It's like buy 1, get 2. Boom. I'm gonna have to cut one of those out so I can go back to BOGO. Every time we learn a derivative now, we're also learning an antiderivative. So if I give you something new, like the derivative of hyperbolic cosine, even though you don't know what hyperbolic cosine is, if the derivative of hyperbolic cosine is equal to hyperbolic sine, then the integral of hyperbolic sine is hyperbolic cosine. It's just sines and cosines, but with different geometry. That was cheating. It's the average of e to the x and e to the negative x is hyperbolic cosine. Hyperbolic sine is the average of e to the x and negative e to the negative x. Here's what's going to happen. Someone is going to come along and say, "Kosh," and you will not do that in my presence. You will say the whole thing. You will just say hyperbolic sine. I don't know why. I cannot explain it. The majority of the world just sees this and says "Kosh" and are okay with it. I do not know why I hate that so much. Because they go over here and they pronounce this cinch. Where's the ch come from? That one I hate even more than kosh. Because some of the people that are like all kosh, cinch, are like all, don't just say tan. I'm like all, where are your rules? Where's your consistency? So I don't like any of these speaking abbreviations. Don't be like all tan KX. Because then you should just pronounce the whole word, tank X. And now stuff doesn't make any sense. Because for for tangent, you're saving one syllable by saying tan KX instead of tangent KX. One syllable. Cosine. With sine, that's just straight up unacceptable. You save nothing by going sin of x. Because it's still just one syllable. Do you know what I mean? So that what's ridiculous is some people are like, well, no, that's sine, cosine, tangent, cosh, cinch. There's no C here. To make it sound in English, you have to have a C. Anyway. Unfortunately, doing it my way implies you not just one extra syllable, but 4 and a whole extra word. Because you have to be like all hyperbolic cosine of x, hyperbolic sine of x. But I may be making too big a deal of it. But considering this is hyperbolic, I think that's totally appropriate to go totally overboard with how I feel about this. Yeah, even though it's not the same. Now I'm leveraging English to my advantage. Hyperbolic. This one is hyperbolic cosine, and this is hyperbolic sine. Cool thing about hyperbolic cosine, if you've got like a chain that's just hanging, suspended, that's hanging under its own weight, that shape that it makes is a hyperbolic cosine. So the hyperbolic cosine function is just the average of e to the x and e to the negative x. So if you've got a chain suspended by 2 points and it's just hanging under its own weight, that's the shape that you're going to get, a hyperbolic cosine. And I'm willing to bet that there are other math teachers out there that will probably probably even say cosh. So already I don't like them, but are against saying cosh. They're like, well, no, you have to say hyperbolic cosine. That get as mad as I do about people saying cosh as people bringing up hyperbolic and using hyperbole, the similarity between the two words. So you shouldn't bring up hyperbole just because you're talking about hyperbolic cosine. It doesn't make any sense to do that. They probably get just as mad as me, like hearing people say cosh and cinch. Here's the rules. You all can't get away with it when you're in my class. You might hear my colleagues say cosh and cinch, and I'll be in the room and I'll find it totally acceptable. There's a reason for that. They're all my colleagues. They have master's degrees. Last I checked, y'all don't. When y'all get master's degrees, you can say whatever you want. Get a PhD, then you never have to have legible handwriting ever again. But right now, as an undergrad, if you have illegible handwriting, that is unacceptable. It's not cute. It's not funny. If you can't read your own writing, you have a serious fucking problem and you need to fix it. When you're a doctor writing prescriptions, sure, your handwriting can be messy. People can die. No one cares. But right now, as an undergrad, it just means you're trying to hide something. I don't make the rules. That's just how it is. Oh, by the way, when you become graduate students, the same rule applies. Because right now, you're just undergraduates. When you're graduate students, you'll just be graduate students. After you get your master's degree, you still won't be PhDs. So you're still second-class citizens. You're second-class citizens forever, by the way. That's just how it is. Eventually, you'll get your PhD, and you say, aha, now I am Dr. So-and-so. And then someone will have a heart attack. Is there a doctor in a house? Oh, sorry, not the useful kind of doctor. Sorry. I studied, finitely generated abelian groups. Will that help? No? We need electricity? Sorry. Anyway, I'm just kidding, PhDs. Calm down. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.